Hello, in this video I will explain about the derivation of Marshallian demand function or ordinary demand function from a utility function. So let me take the uh, normal case of nice shaped indifference curve. So this means we take a simple case where the indifference curves have the convex and downward shaped. So such indifference curve can be represented by a Cobb-Douglas utility function. Let us assume the simplest case utility of x and y depends upon x times y. So this is the simplest example of a Cobb-Douglas utility function. So let us assume that price of x is px and price of y is py and the consumer's wealth is w. So the consumer's utility maximization program can be expressed as maximize utility equals to x times y such that his budget constraint pxx plus pyy equals to w is fulfilled. So since this is a constraint maximization problem, we make use of the Lagrangian function and derive the demand function from the maximization technique. So the Lagrangian function can be expressed as L, which depends on x, y and a new variable lambda equals to the utility function xy minus lambda times homogeneous version of this. So this is pxx plus pyy minus w equals to 0. That is pxx plus pyy minus w. So now we take the first order condition for maximization. The first order condition for maximization, it requires that the partial derivative of L should be 0. So the partial derivative of L with respect to x should be 0. The partial derivative of L with respect to y should be 0 and the partial derivative of L with respect to lambda should be 0. So this gives partial derivative of this with respect to x is y minus lambda px is 0. This gives us x minus lambda py is 0 and this gives us the budget constraint pxx plus pyy minus w is 0. So by simplifying these two equations, dividing first by second, we get y over x equals to px over py, or y equals to px over py times x. So we use this relationship and we substitute this relationship in the budget constraint. So this is px times x plus py times the value of y from here is px over py times x minus w is 0. So this is nothing but 2pxx equals w, or x equals to w over 2px. So this shows the quantity of x as a function of the parameters, as a function of the income level and as a function of the price of x. So this is the ordinary demand function for x commodity. So we can now derive the demand function for y commodity by simply substituting the value of x in one of the two equations. So now let us substitute Let us substitute the value of x. Let us substitute the value of x in this equation. So we get y is px over py times the value of x is w over 2px. So px gets cancelled and this gives y equals to w over 2py. So just like the case of x, this gives us the quantity of y as a function of income and price level. So this is the Marshallian demand for y commodity. So now we can write both the demand function in one place as simply x x x. So the quantity of x depends on prices px, py and w. This equals to w over 2px, and the quantity of y, which depends on also prices and income, is w over 2py. So these two are called the Marshallian demand functions. Marshallian demand functions for x and y commodity. So finally, let us discuss some properties about these demand functions. So there are 3 or 4 properties regarding these demand functions. The first property regarding this demand function is that the demand functions are homogeneous of degree 0 in prices and income. So it means that if you double prices and income, quantity demanded remains unchanged. So homogeneity of degree 0 means that if you increase all the variables at same rate, quantity is unchanged. So you can see in the demand function that if we increase w by 10 times and px by 10 times, this gets cancelled and the value of x is same. So the second property of this demand function is that the demand functions are non-decreasing in income level. That is, quantity demanded with respect to income is greater than or equal to 0. So with the increase in income, quantity demanded won't go down. So we can find the derivative here. To validate this. So del x over del w, this is 1 over 2px, which is greater than 0, and del y over del w is 1 over 2py, which is also positive. This means that with the increase in income, quantity demanded of y goes up and the quantity demanded of x also goes up. So now we go to the third property. The third property is regarding the relationship of quantity demanded with its price level. So the third property is that the demand functions are non-increasing or decreasing in on price. So it means quantity demanded of X with respect to price X, this is always negative, and quantity demanded of Y with respect to price of Y is negative. So it means if price goes up, quantity demanded will fall down. So we can find this derivative in this demand function, which is minus W over 2 px squared, and this is also W minus W over 2 py squared. So these are negative. So the fourth property of this demand function is about elasticity. So these demand functions have unitary price elasticity. To see the picture of elasticity, we take natural log in the demand function. So this becomes log x equals to, this becomes log w minus log 2px. So this can be further expressed as log x is log w minus, so this is log 2 minus log px. So now we differentiate log x with respect to log price of x, and its value is -1. So this differential operator, this shows the percentage change in quantity demanded of x due to percentage change in the price of x, which is nothing but price elasticity. So this is EPX is 1. Similarly, we can expand the quantity, so the demand function for y in this way, and we can show that del log y over del py is also -1. This means price elasticity of y is 1. So in this way, the price elasticity in this demand function is unitary. So finally, the last property of the Marshallian demand functions in this case is the zero cross elasticity. So zero cross elasticity. So zero cross elasticity implies that if price of x changes, there is no effect on quantity of y, and if price of y changes, there is no effect on quantity of x. So we can solve this by simply differentiating the demand function by taking log. Just we did it few minutes ago. So by taking log, this demand function becomes log x equals to log w minus log 2 minus log px. So if you differentiate log x with respect to log py, so this is nothing but the percentage change in quantity demanded of x due to percentage change in price of y, which is the cross elasticity. So this becomes 0 because there is no price of y parameter here. So what this shows is that if price of y changes, there is no change in the quantity demanded of x. Similarly, we can show that change in the quantity of y due to change in the price of x is also 0. So this is called the zero cross elasticity. So thank you for watching this video, and please watch my next video regarding the derivation of compensated demand functions.